Good afternoon, ladies and gentlemen. Welcome you to the lithium-ion battery technology and recycling session. We have 4 speakers for this session, and each talk will be about 10 to 12 minutes. Please be aware the session is automatically recorded by the conference host. Our first speaker is Asif Mahmood. Asif received his PhD in material science and engineering from Peking University in Beijing. He worked at University of Sydney for 3 years before joining University of Technology, Sydney as a Chancellor's Research Fellow. His research interests include nanomaterials for electrochemical processes and rechargeable batteries. He has published over 80 research papers in high-quality journals. He won several awards, including an exceptional award for academic innovation, International Students Academic Award. Lately, he was recognized as the Higher Education Rising Star 2020 by the Educator in Australia. And he has also been recognized as one of the top 2% highly cited researchers in the world. Welcome, Asif. Thank you.
Thank you very much for giving me the opportunity to speak at this conference. My name is Asif, and I'm currently working as Chancellor's Research Fellow at the Center for Clean Energy Technology. I will use CCET in short form for this center. My work actually is related to material fabrication for batteries. And because of the theme of this conference, I'm presenting one article at the end of my talk related to this conference, but mostly my work is about fabrication of materials. At UTS, we are working towards the development of efficient devices for energy harvesting, storage, and conversion. We are developing efficient catalysts for energy conversion processes, especially hydrogen production, but mostly our research area is towards rechargeable batteries. And in rechargeable batteries, we are working on lithium-based battery chemistries like lithium-ion batteries, lithium metal batteries, lithium oxygen batteries. And even beyond lithium chemistries, we are working on sodium batteries, as well as zinc batteries and other battery chemistries. So a range of different battery chemistries, but in this talk, I will primarily talk about lithium batteries only. Before going into detail about the talk, let's firstly have a look at the current standing of batteries in the international market. So if you see this picture, you can see the major battery manufacturer in the world is the company CATL, which is providing the batteries to giants like Tesla, BMW, Volkswagen, etc. And that shares nearly 34% of total battery fabrication in the world. The next competitor is LG, which is 14%, nearly 20% less than the CATL, and then 12% BYD. These CATL and BYD are Chinese manufacturers. So you can see the bigger share coming from China and also these smaller ones as well. So if you just see the top 4 manufacturers, they are sharing nearly 70 to 75% of total battery manufacturing around the world. And the rest is smaller companies. And although batteries can be used in a range of different applications, but if we just look at the electric vehicle, if we just compare that one, you can see that almost all big vehicle manufacturers are now manufacturing electric vehicles. And if you go to the right of this picture, you can see Tesla. And Tesla is now nearly 25%, sharing nearly the EV market. And alone Tesla market value is more than next 4 competitors combined: GM, Ford, Volkswagen, and Mercedes. So that gives an idea like which company is doing what and which company is making the best batteries at the moment. Anyways, now let's have a look at what batteries actually consist of. I will talk about the chemistry a little later, but as a general idea, batteries consist of cathode, anode, separator, and electrolyte. By weight, if you see 50% of battery is basically consisting of cathode. So if we can improve the performance of cathode, you can just see how much improvement we can have And cathode is the side which have lithium as well. So that's one of the limiting factors as well from future perspective. If you go by weight, compare by weight, you can see graphite, which is normally used on anode, constitutes nearly 52 kilogram in a normal vehicle battery stack. In this picture, I'm interested in talking about lithium and cobalt. You can see lithium is nearly 6 kilogram and cobalt is nearly 8 kilogram. Cobalt is very expensive, as we know. Lithium is also very expensive. And if we just have a general look at this picture, we can see after the using this battery, let's say for 10 years, 15 years, after the lifetime of the vehicle, this battery stack can be resourceful for next generation if we can recycle it. So if we can recycle, we can get a lot of components from one car, electric vehicle, including graphite and other elements, but most important, lithium, cobalt, and this type of metals. Now, batteries can be configured in a number of ways: coin cells, cylindrical batteries, pouch batteries, and then they can be stacked together to get higher efficiency. In the labs, we generally assemble coin cells to test the material performance, but we can also assemble pouch cell as well. Now talking about chemistry, so the batteries, whatever configuration we want to assemble, they always consist of cathode, anode, and electrolyte, separated by the separator as well. And now this gives us flexibility in designing the materials, like for anode, mostly carbon materials, but transition metals also explored in last 10, 15 years. Cathode materials are mostly compounds containing lithium, lithium-rich materials mostly. Electrolytes, liquids mostly used previously, but now people looking at solid electrolytes. So my research is mostly related to anode materials, but our center is working on anode, cathode, and electrolytes. So I will briefly introduce all the research. So let's have a look at the anode materials, which I have been working previously. In this work, for example, I wanted to address two issues. One is to improve the efficiency, and second is to improve the cyclic stability. Now, one of the key issue with graphite is that it has lower efficiency, 372 milliampere hour per gram. If we can introduce transition metals, they can perform very well. They can give very high capacity, but they lose performance very quickly because of aggregation, because of pulverization, volume expansion. So we tried to fabricate the graphene tubes. Now, these are different from carbon nanotubes. You might be familiar with carbon nanotubes, but these are familiar, as you can see here. We wanted to increase the internal diameter of the tube and then load the transition metal species inside the tube so they can be protected from the electrolyte and they can still provide the charge and discharge. So you can see here, these particles were then loaded onto this large diameter tube. And to further stabilize, we created empty spaces inside the particles by a second heat treatment. This provides enough space for reversible volume expansion to the particles. Together, these hybrid materials delivered very good capacity, around 1,400 milliampere hour per gram. That's nearly 4 times than graphite, and also very good stability up to several hundred cycles. Just to say, like, there is a flexibility in material design. We can design materials in a number of ways. This is just one of them. Then in another experiment, we wanted to see how much active material we can load. Generally, we see that we can load more active materials, we can get more performance. But we wanted to see where is the limit, how much active material is the best one, whether it can perform if we go 5, 10, 15, 20, it always keeps on increasing or not. So we chose the layered material like molybdenum selenide and loaded onto carbon nanotubes. So we controlled the loading mass to 5 layers of molybdenum selenide, 10 layers, 15 layers. And if you see this figure, you can see that when we go to 15 layers, the performance increase, but after 20, 30, or 40 cycles, the performance degrades very quickly. This means that although with active mass increase, we have increased performance, but it's not stable. With 10 layers, we got the optimum performance, and it's very stable up to 100 cycles. So it means that active mass has to be optimized, and only then we can get a better performance. Moving on, our group is also working on metal batteries, metal anodes. Now, these are different from traditional anode materials like graphite or the materials which I just introduced. If you see this figure, you can see that graphite can deliver 372 milliampere hour per gram. In comparison, lithium metal anode can deliver 3,800 milliampere hour per gram. This is nearly 10 times higher than graphite. So if this one can be utilized, this could improve performance to much higher level. But one of the key issue with metal anode is the dendrite formation, and the dendrites actually pierce the separator and cause short circuiting. The batteries don't really work very well. Our group reported many articles, but I chose 2 articles to show here. One is the temperature controlled stabilization of lithium metal anode, and the other one is using a polymer additive in the electrolyte to stabilize the interface both on anode and cathode. So for first one, we found that if we use high temperature for testing, like for example, 70 or 80 degrees centigrade, only the temperature is sufficient factor to stabilize the reversible stripping and plating. We don't need anything else. So for example, if you see this figure, this battery is tested at 20 degrees centigrade. So there's a lot of dendrite formation. This battery is tested at 60 degrees centigrade. So it is more homogeneous after 720 seconds. There are other characterizations as well, but this is the only space I have at the moment. Then we also use the polymer additive. So polymer additive actually stabilize the interface. The interface, once stabilized, it can protect the metal from formation of individual species, islands, which can eventually grow into dendrite. So if we have stable interface, that can prevent the dendrite formation, and then the battery can cycle very stably. And also the polymer can prevent the the battery from getting fire. So it can not only increase cycling life, but also prevent battery from getting fire. Anyways, so these are different ways, other ways as well. Then our group is also working on lithium sulfur batteries, lithium selenium batteries. Sulfur is a very attractive cathode material that gives much higher performance. But one of the key issue with sulfur is that the polysulfides dissolve. Sorry? Okay, then I will go to the paper which I want to talk about. As we can see, lithium prices are increasing. So our group very recently reported a methodology for lithium extraction from spent batteries. So in this one, this is an example for the cylindrical cell. So if we open a cylindrical cell and then this electrode is passed through this setup, this setup can extract lithium, and then that lithium we can get as lithium hydroxide in the end. So what we have here is a solid electrolyte basically in these columns. That solid electrolyte is exposed to the electrode. So the lithium from this electrode moves through solid electrolyte, and then lithium hydroxide solution is passed through this column. And that one dissolves the lithium that is transporting from this electrode through this column to the liquid. And eventually we get this high concentrated solution. This is a very attractive methodology. So this is how it works. I don't know if the video is fine or not, but this is a very attractive method because we don't need any pretreatment. We don't need any high temperature, any decomposition. So basically the electrode surface is maintained so we can extract other metals later. But at the moment, we can directly get lithium. We don't need to do anything. We simply pass our electrodes through these columns, and then we can get the lithium. So that's the idea from this paper. And if you go by cost, so basically it can deliver, starting from $1 battery, it can deliver up to $11 materials at the end. And this is the cover picture that we presented. And of course, we want to reduce cost and increase the performance and increase safety. So because of short time, I'm very sorry, I have to be very fast, but these are some of the facilities we have. And I want to acknowledge the institutions where I studied and worked. Thank you very much. Apologies again, I had to be really fast.
Is there interest from manufacturers for that? Oh, sorry. Is there interest from the manufacturers directly now? Just because end of life batteries are much harder to dismantle, and we don't have manufacturing in Australia. Can that also be used on LFP batteries?
Yes. So basically, if you see, Yeah, here. Because of what time I could not explain. So we tested on a range of different cathode materials.
Yeah,
so
because
basically LFP is one of them.
I think that manufacturing might come here. That's fine.
Should be.
We have quite a lot of audience online around the globe. Is there any question from the online audience? You can mute yourself and ask questions.
I went too fast.
I have a question for you. So, you mentioned doping some micro ability of animal. Do you think the transition of the animal?
They can be, yes, they can be, of course. Similar method can be used, but other ways as well. Should be. Yeah. Yes, yes, yes. Yes, because solid electrolyte, which is used in this process, is basically compatible with both anode and cathode. So can be used with both. Thank you very much.
Our next speaker is Rory McCallum. Rory is a PhD candidate with CSIRO and the Swansea University of Technology. After 15-year experience in the electrical and the solar industries, he joined CSIRO in 2017, completing his undergraduate and honors before starting his PhD. His work focused on the development of novel electrolytes using natural product-derived solvents. Welcome, Rory, for his talk.
Hi, can you hear me?
Can you share your desk?
I have to wait for the other screen to stop sharing, it's saying.
Can you help me? There's a mouse. Stop sharing. Okay.
Yep. Okay, you seeing that now?
Yes, we can see you.
Yes. Hi, my name's Rory. I'll be presenting my research into the development of novel and safe electrolytes. Sorry?
All right. Yeah. It's still not, no.
Still not?
We still can't see your slides.
Okay, I've been doing.
But there's a slide already saved in this computer on the desktop.
How's that?
You have to change the slides by yourself. Now it's
working?
All right, it's working. All right, it's all yours.
Okay. So yeah, I'll be presenting my research into the development of novel and safe electrolytes from bio-derived solvents for lithium-ion batteries. My supervisors are Adam Best, Peter Mann, and Thomas Ruether from Swinburne and CSIRO. So if we just look at where we've started, I'm going to give a bit of a background and then just a small bit of information. But we've gone from 55 watt hours per litre in 2008 in terms of energy density up to 450 watt hours per litre today. And that's mainly been driven by a little bit of chemistry in the cathode and a lot of engineering. But all of this has relied mainly on cobalt-based cathode systems. Although we've slowly decreased it, we're still using cobalt and with nickel. And that cobalt is mainly mined in the Congo, and it's a limited resource. We're running out of it. So yes, for recycling, it'll be very important. But also looking at other chemistries will be very important that don't use cobalt. So if we look at the basic design of a pack, we used to develop these kind of cell, module, and then pack technologies where we got small cells, like 18650 cells, built them into modules and stuck them in a pack. The problem with these was that they weren't very energy dense. And so if you look at some technologies where only 20% of the whole pack was battery. And now we've moved to this more cell to pack design. So the KTEL, BYD have both moved to this kind of technology where we build single cells as big as a pack, and we get much higher energy density. So we can have 80% of the pack now just battery cell. LFP is preferred, especially in China because of safety requirements and because they have access to LFP is the main reason. They don't have cobalt. But it's more thermally stable, so you can get even higher energy densities than you can relative to the original cell density. Recently, Nature's Sustainability Expert Panel released a report in May, and there's a few key things that I found within the report. One of them was the need to replace LiPF6. It's quite toxic to produce. You have to use HF and a lot of other nasty chemicals to produce it, and you've got a problem in the PF6 when recycling it, that you can possibly produce HF gas. So that's one issue, and the need to remove cobalt because of the negative health impacts and environmental impacts within the Congo, where about 50% of the cobalt currently comes from. They also spoke about the need for less flammable electrolytes, just so that they're easier to handle and don't result in as many fires, and then therefore spilling potentially toxic chemicals after the fires. So one of the big issues with fires is the thermal runaway process. So just to explain briefly what that is. So we have some kind of mechanical, electrical, thermal event. So this can be piercing of the cell, deformation, overcharging, over discharging, or just heating the battery up too much. This leads to decomposition of the SEI, so it's a kind of protective layer that makes lithium-ion batteries possible. It's on the anode, and then the anode starts to react with the electrolyte. We get further increases in temperature. We get the separator decomposing potentially, and then we get the cathode and eventually electrolyte decomposition. So if we can stop any of these steps along the way, we can really limit this thermal runaway process. And this is one reason that lithium iron phosphate is preferred, because it's less likely to decompose. But this is at about 100 degrees that this starts to happen. And we can see one of the results here. This was the Tesla battery fire pack in 2021. And yeah, the whole thing caught on fire, and this was a cooling issue, I believe. But if we just look at what happens if we heat batteries up to 60 degrees, this is well below the limit of getting to these thermal runaways. We see increases in graphite intercalation and solid state diffusion. We also see electrolyte conductivity increase by almost double. And so this leads to a much faster charging and discharging cell. It also means that we go from around 2000 cycles, if we charge it at 1 hour charge, 1 hour discharge, to around 250. And this is because of the growth of chemical reactions at the anode and the SEI layer, or the protective layer of the anode, and just ultimately decomposition of the electrolyte. And this also increases fire risk. So there's some big issues. But what happens if we just heat it whilst we're using it in an EV situation, where most of the time they're just stationary? Well, we can see if we take an LFP cell and do this, we get really high driving ranges in all conditions. So this is the red line you can see versus the blue line for just the standard LFP cell. And we see high power delivery under all conditions. It only uses about 2 to 4% of the battery pack to heat it up, and we can charge them in 6 minutes. So, and this is just using standard off-the-shelf LFP cells. We've still got lower energy densities than NMC. Still got flammable electrolytes, so if something does go wrong, they are still flammable. So if we look at some other electrolytes that are used at high temperature, we have the ammonium, phosphonium, boronium ionic liquids, and these all perform well at high temperature. They only perform well at high temperature generally. And there's a cost issue, though, often associated with ionic liquids. If we look at additives, we can look at fluoroethylene carbonate. That's often used as an additive and helps prevent SEI decomposition. And high salt concentration and bisalt systems. So we can think about water in salt electrolytes, or we can use these DME with bisalt systems. And here we can see we can get conductivities actually higher at those higher temperatures than even the standard electrolytes. So, but they're still quite flammable. And of course, solid electrolytes, which are always only a couple of years away, the kind of the fusion of battery world. But supposedly it's only a couple more years till we have a working product. But they also have some very good safety characteristics potentially. So my project is focusing on natural and naturally derived solvents. And some of the key benefits is they can be made from biomass. So you can think of lignin and cellulose, for instance, can be used to make some of these solvents. And they can be a really low cost. We're talking down to $1 a litre. I mean, obviously we're going to have high purity solvents, but you know, $1 a litre for 99% purity is pretty good. We have a diversity of chemical structure that's really hard to synthesize. So if you look at nicotine here, we have like the building blocks of a pyrrolidinium there, and we see similar melting and boiling points to, you know, some of, or close to that of some of our ionic liquids. We know what the toxicity is. I mean, nicotine is, you know, arguably the most dangerous chemical on the planet, but we know how it's going to function, and they've been previously tested. Styrene, on the other hand, here is quite benign and is a good replacement for NMP in an environmentally sustainable way. There are always challenges when using naturally derived solvents. Electrochemical stability is probably the key one for batteries. You know, we kind of know what we're looking for to get that stability, but once you mix it all in a solution, everything changes. We have issues around solubility, which have to be tested. And we have to make sure these are able to be produced at scale and purity. You know, you often see papers where they're using $3,000 a litre chemicals, $3,000 a gram chemicals. You know, it needs to be something that we can get from a common plant or a common source, not some rare Himalayan flower or something. It needs to be quite accessible. So the aims of my project have been to develop an electrolyte system that will deliver that high pack level density by solving the kind of thermal runaway issues or solving some of the engineering problems with chemical solutions rather than the other way around. And to make electrolytes that are greener, safer and cheaper, hopefully, than current technology. I'd like to thank Swinburne University and CSIRO for funding my PhD. Thank you.
Thank you very much for Rory's wonderful talk. It's spot on 10 minutes. Thank you very much. Is there any questions from the floor for Rory? Any question online? You can mute yourself and see your name and company. Still thinking. we'll just wait a few seconds, just in case. All right, we move on. Our next speaker is Andrew Mackenzie, the Managing Director of Envirostream, based in Melbourne. Envirostream is one of the most famous Australia battery recycling company, a subsidiary company for Lithium Australia. Thank you very much for coming today, and welcome. It's all yours.
Good afternoon, everybody. Thanks, Rory. I'm going to try and I hope I don't hang up on you. You're still on the screen. Oh, there we go. We got it. Yep, all good. And then, sorry, down me. Yes, yep. So good afternoon, Andrew from Envirostream. Thank you for the very nice introduction. We're famous, I think, because we're the only ones. So we're still the only licensed facility, and we're very proud of that. And we're new to the industry's new. It's a new space, so it's hard. It's good to be welcomed with such kind words. So mindful of time, I will speak quickly on a few topics, but there's a lot to cover. We won't be able to go into the technical parts of everything, but please, hopefully there's some questions you have at the end. So this is not in presentation mode just yet. Sorry, Thomas, slideshow. We're good? Okay. Yeah. All right. So our industry is changing very quickly. We started with electronics, mobile phones, power tools, these things. As Asif pointed out, there's new batteries coming. We don't want sulfur batteries, thanks. We like the lithium as it's able to deal with it, but we're now diversifying into electric vehicles, energy storage, heavy vehicles. We know this is coming. But unfortunately for Australia, the complication at the moment is dealing with the mess you see up on the left-hand side is collection from households is what we've got today. And it's a real challenge for us and the industry going forward. Is we've got to get that right before the other volume lifts. And that's what our challenge is. So what we offer to the industry is the solution for collection and management of these batteries. So we don't want batteries to go to landfill. We all hear the news of fires in landfill and curbside collection. So because we're focused on the end of life of small batteries currently, we've looked at the management of that first, and we're developing our ways to deal with the big batteries and how those consumers will be serviced in that area. So from small collection units, because of the size of a large collection unit, just to risk mitigate is how this all sort of started. So when you've got large containers full of batteries, we have a large risk. So we've developed small containers for retail type of collection, and then transport through to larger pallet size units for storage and safer service sort of offerings is to customers. So this is sort of the first step to a recycling business, is how do you move these things around and how do you make safer the collection is how we offer that. This is the problem next, is now we have to deal with transport. So transporting batteries in Australia is difficult because they have to move far. They're not close together, like maybe at a mine site or something. We can say we've just got a large deposit of lithium or cobalt would be nice. However, our problem is now looking at logistics, and this is going to grow. If we've got EVs, small volume of EVs in Australia, how are we going to manage those from the car service centres back to recycling centres? So this is the next challenge. It's nice to have, technical sites. They're very expensive. If we do model on what's happening in Asia, China, Korea, they're 40,000, 100,000 ton plants already because they've got that waste from production waste. We don't have that. We have end of life waste. So we've got a lot of other tricks to manage in Australia that it needs to be built awareness around that because it's a charge that we haven't even pulled the battery apart yet, and we have got these problems. So next, this is the opportunity. So those are the problems in Australia coming. This is the opportunity that's coming. So waste arising is the first two charts in the background, is volume of battery sales is how this is calculated. So this is an independent source. I'm not even sure if it's CSIRO, so I won't mention who it is, but this is some work being done by federal governments and stewardship bodies to look at the waste that's coming. Batteries have been a priority waste from the federal government for the last few years, so this is why. So we're looking roughly at about 2030 to have 100,000 tonnes of lithium batteries as waste. So that's what we've got to get ready for. The chart there in the middle is the lithium demand and why the mining industry is so focused on expansion at the moment is because they can see there's a huge shortfall. By the time you get to 2030, there's a lithium shortfall that they're flagging in that gap. And it's also with nickel, it's also with cobalt, it's also with graphite. So we see ourselves from that waste arising in Australia is if we can capture the stream of material, if we can then dismantle it, get rid of the plastics, and we can then manage the anode and cathode, we hope that we're the solution to help fill that gap. Otherwise, this is not a circular business at all. And that's what we have to be mindful of, is to get brand awareness, get the people who are responsible for bringing batteries to the country, managing it better, because it's difficult here. So if we really truly want a circular economy for batteries, it's the cathode and anode powder that are circular, anode maybe not, but that's what our plan is. So how we do it, again, more regulation. We've got to move these batteries under dangerous goods. We've got to be very careful and mindful that we don't use conventional waste transport, whether that's scrap metal, whether that's household. So it's, again, tricky. Sorry to harp on it, but I need to make sure that there's any brands listening. They do take care of how that ownership works. You can't pass batteries onto the household and then expect that the household has the equipment to manage that properly. Whether it's a scooter, an e-bike, an electric vehicle, we're very mindful that this is a tricky product to move. We now have to be careful at our end. So when we receive batteries, we can't just be a bit flippant and say, oh, they can go to anybody who can recycle, because there's been multiple battery fires in factories that have burned to the ground through large stockpiles. Under the EPA rules now, we have to have for every 4 tonne a way to manage that with fire rated walls. So that has to be that dark green area in our factories. We're only allowed to store 4 tonne of batteries in each zone. That's how the EPA, the Environmental Protection in Australia, is looking at batteries. So again, this is a cost to the recycling industry to make sure that recycling is done effectively. We still haven't processed the battery yet. So this is the process. In short, just mindful of time. The hazards that we've got to deal with further other than fire. So discharging batteries, we don't necessarily discharge all batteries because there's a lot of IP ratings in IP67, so they're waterproof. There's often people putting batteries in salt water to discharge the energy was the first sort of en masse discharging. There's electronic discharging, all these different plugs, so it's a bit tricky. We don't have nice cells, 18650 cells. We have packets of batteries. We have the module of batteries. So our process is to shred the battery, fully charged. We can't rely on it being discharged. So we assume that all batteries are fully charged. So we do deal with the heat. The heat creates the HF gas. We also deal with the HF gas in our scrubbing towers, and we have to be monitored by our EPA as well. We're then able to shred the body of the battery to extract the cathode and anode powder. And again, that's something that we've developed quite a unique process because we don't have production waste. So we've got great partners in South Korea with some of the big production waste recycling facilities because we've developed the process for end-of-life batteries versus their process that deals with production waste. So here we have some of the contents of the mix, because we're not just dealing with 811 or 622 or LFP chemistries or NMC or just LCO. So we've got a mixture of batteries. So our product does fluctuate in what you get. And that's why the questions to Asif was, yeah, it's nice to have that process. Unfortunately for us, it can be tricky, but that's why I asked, it's good if you're looking at different chemistries, because as a recycler, you can't, you got to mix, you've got to mix. So again, we now through the fire and the discharging of, the control mechanisms we have for cooling that down so we don't create more HF gas. And if we create a hot product as we go, we also create, there's some talk of vapor clouds and things like this that batteries are generating. You see those on YouTube. There's fire research being done when batteries are charged at about 85, 90 degrees, an LCO battery will let a fume out. So we're also dealing with hydrogen gas and a few other products because if we get it too hot. So we have to cool everything down and we just use water. The water then absorbs a lot of the fluoride and we captured a lot of the lithium there. So we've done some treatment of that water with CSIRO. We can throw you in the promotion. And we've created a lithium phosphate product which was reusable in LFP batteries. So we've had quite a good success. I think we made couple of button cell batteries, but the process is there and it's developing. The other is the organics from the battery chemistries that we have to clean out of the water before we can reuse it. So the water that we do clean, we can then create a small waste stream of, we've got lime and a few other solids that we use for extraction of that process. That is what, oh, sorry, I should step back a sec. So what we create is the anode and cathode mix. So in Australia, we don't have a hydromet process. There's technology to prove that it works and you can do it. However, we do have to be realistic. We only have a small volume. So even if we had all the batteries that were available today, as far as end of life, we're looking at about 3,000 tonnes. So if we could get all 3,000 tonnes, we'd only have about 1,000, 1,200 tonnes of MMD, mixed metal powders, mixed metal dust, black mass. It's called a few things, but it's essentially the cathode and anode powder of the battery. So we sell that onto the market to South Korea currently, and they will extract further nickel sulfates, cobalt sulfates, lithium carbonate, and sell that back to the battery market. So our cathode powder, we know that's circular. Some of the graphite is lower value, so lower percentage than what's reusable in batteries. So that will go to make electrodes and everything or lubrication. So mainly electrodes for arc furnaces or lubrication industries. The copper, the aluminium from the foils, we can sell into the local scrap market and that gets reused for metal recovery. So that's really it from me. I know I'm trying to talk fast, but hopefully there's some questions and then that might also give, I'm not sure if Thomas is online, but if he's got some extra time. But that's us in a nutshell. It's a tricky industry. It's a growing industry and we're really thankful to be here today and to present. And yeah, if there's any questions, happy to take. Yep. Yep. So there's a couple of, yes, we've had some incidents because button cell batteries are the worst. So surprisingly, everybody's worried about the lithium from power tools and everything, but unfortunately, there's been a product recall of button cell batteries. And when you get two of those together and they get hot, they will, maybe if there's a power tool battery in there, they'll start the fire. So limiting the weight was the biggest success. And then that bag is actually 2 layers of essentially a fire blanket, which is rated to not burn. And then it depends on where it is. So if there's lots of them on it, the silly thing is for the dangerous goods transport, we need to put it in a cardboard box. So the boxes are catching fire, not the bags. And so the material inside does burn, but it'll manage in there because it'll run out because there's not a lot of load. So there's only 15 kilo maximum. And that's of, say, a mixture of alkaline lithium batteries, nickel metal hydride or other types of chemistries. So there's not the same fuel if it was just one bag full of lithium, and that's helping a lot. So it's also that mix that's helping mitigate the risk. But it's not necessarily, the bag survived the fire, but we know we've got to use a box to meet dangerous goods transport. And then what's next to it is, without hinting that maybe what next to it caught fire, that's the problem. And that's where transporters are going. We just don't want batteries. So we're trying to keep them happy and it's difficult. But then moving into the pallet, that's got a testing we're trying to get 2-hour firewall testing because that's the same at the factory. So that would give someone enough time that box, the radiant heat from that and all those things, we've got to be rated for 2 hours that it won't pass that fire on. So that's for us like a service center for e-bikes and power tools, that sort of thing. Yeah. Yes. So that's a trick. Thank you, Rory. Now I'll throw you in because of the photo of the Tesla battery. That was a trick to dismantle. So we had to clean that up. So we had to remove it from site, and we had to do that using vacuums, and because you couldn't expose people to the problem. And then that would be a direct feed into our factory. It was fine. It was still a recoverable product. However, Tesla, again, they glue everything together. They're filling up the battery full of silicon so it doesn't get moisture in under the car. Great idea, not for dismantling, you know, and so it's really tricky. It's really tricky. So if we build a shredder big enough to throw it in, I don't know if we could cool it down as a product, and then we've got to deal with big, thick steel and things in the shredder where we're only trying to chase cathode powder. So it becomes a very tricky question to answer. At the moment, we're doing it very manual. And that's the only way to do it. We will take a pack from a car, a bus, a truck, and dismantle that to the pack level, and we'll deal with the pack. Because even the big packs from the, they might go to about 40 or 50 cells per pack. Forget which is the pack and the module. But the 40 or 50 cells we can deal with, no problem. Yeah, yeah. Yep. No, so we only send the cathode and anode powder. So that is just how like scrap metal works. If you were selling aluminium, you have to sell it overseas to a smelter. The shipping is not that expensive. We've also tried to send it to Kalgoorlie. Costs 3 times as much to send it to Kalgoorlie as it does to Busan in Korea. So again, transport is the problem in this country. It's just how you manage this, how to do that. It's not a hazardous waste. It's toxic. It's got some ratings, but it's not under the Basel permit because it's no longer an electronics waste. So we've not got around the rules, but we understand the rules to say, okay, we're in this market here, and it is a product essentially. Yeah. So it does get a bit easier to ship.
Our last speaker is Thomas Ruether. He is a senior research scientist and the team leader for electrochemical energy storage at CSIRO. Since joining CSIRO's Energy Business Unit in 2006, he has been working on many aspects of lithium battery chemistries and recently focused on questions around the sustainability and the recycling of lithium batteries. Welcome, Thomas. I'll hand over to you.
Yep. Will someone operate my slides or because I can't advance them here?
Stop sharing so you can share your desktop. Stop sharing. Okay. You can share. Yeah, you can share your desktop.
Yeah, anyway, thanks for the opportunity to speak at this event. And thanks to Yanyan, my colleague, for the kind introduction. To begin with, I like to make a case for batteries. There are 2 prime reasons. One is electricity generation, which is, electricity consumption in Australia is very high, 200 terawatt hours per year, which accounts for about 30% of carbon dioxide or total emissions, because it's mainly generated from oil and gas, coal and gas utilities.
Excuse me, Thomas, can
yes?
you click the PowerPoint?
Oh, yeah, sorry.
Mode so it's bigger.
Thank you. All right, yeah. And I will try to use, where's my pointer options here, laser pointer. Given that Australia has the best solar and wind conditions globally, it would make sense to generate this electricity from these sources, which until recently has been difficult and due to the lack of a proper storing system to deal with the intermittency. But given the rise of electricity generation from renewables, the installation of large-scale batteries, electrical energy storage systems has risen quite significantly, as you can see here on this map. The second reason is transportation, which accounts for about 10 to 15% of overall emissions. So electrification of the vehicle sector is needed and now possible with modern lithium batteries. In terms of circular economy and sustainability, the obvious questions arising are: how do we deal with the emerging waste streams for batteries? Do we have an end-of-life strategy for it? And what is the environmental impact of producing lithium batteries? So the working principle of commercial lithium-ion batteries is based on the use of metal oxides from cobalt, nickel, manganese, and in the future more iron, and an electrolyte system which is flammable, combustible, and very corrosive. And this causes many concerns around limiting supply of resources, the environmental impact or footprint of these devices. High temperature processing is involved, and the production costs can be very high. And so to deal with these concerns, change is needed for how we source materials, how we manufacture them, how we choose them, and how we handle the end of life of the devices. So this slide shows some analysis around the environmental impact. Around 40 kilograms of carbon dioxide equivalents are generated for a 1 kilowatt hour battery. And the breakdown here shows that for making these batteries, 40% of the emissions come from cell manufacturing, and quite a high 30% of these emissions come from the making of the cathodes with the which hold the metal oxides. The inset here shows how carbon dioxide emissions are changing or depending on the energy system at the production site, and how they are dependent on the battery chemistry. So here's a good case for iron phosphate batteries, which have a much lower percentage of carbon dioxide emissions. What's concerning the sourcing of the required materials, the US Geological Survey has raised serious issues in this regard, because the predicted lithium battery market will rise to around 3 terawatt hours in 2030, requiring about 2 million tons of nickel and cobalt. And for the info here, lithium hard rock mining produces about 15 tons of carbon dioxide equivalents per ton of lithium. With these background facts around the rising deployment of lithium batteries and their potential environmental impact, CSIRO's long-standing lithium battery research group in Melbourne has developed projects around the lithium battery recycling 4 years ago. After the common prelude phase of surveying the landscape and including stakeholder interviews, we came up with 4 key areas to invest in. 2 electrical portfolios addressing second life reuse and the battery discharge, and 2 chemical portfolios to address the various steps in the lithium battery recycling pathway. So the current key focus areas, what we're doing at the moment are around the second life reuse of batteries and the recovery of the lithium salt in the batteries. So this slide shows a common or most practiced recycling process, which starts usually with the shredding the modules or cells, then producing these shreds, which will then go into a sorting stage where we separate out copper, plastic, aluminium, and obtain the black mass. And we heard from Andrew quite a bit about this. The black mass consists mainly of the electrode materials, graphite, and the metal oxides. Some of the processes, they also take this a little bit further and recover the high value materials, cobalt, nickel, and lithium, and also graphite from it. So what we're doing at CSIRO is to look at processes which are coming in at the front end of existing lithium battery recycling processes. The second life reuse is done for EV packs, which typically still contain 70 to 80% of their original capacity, and so they can be principally reused for other applications. For the purpose of extending the battery pack's lifetime before it enters the battery recycling, CSIRO has developed a versatile battery management system which allows to perform a health check on entire battery packs without completely disassembling them, which would be very labor intensive and therefore prohibitive. So the picture here shows our 5 kilowatt hour system. It's a demo system currently set up with 10 nickel metal hydride Toyota Camry battery packs. But because our battery management technology is battery chemistry agnostic, it can also be used for lithium batteries. So the value proposition of our lithium salt recovery technology has a monetary and material use aspect. The material use in the material use aspect, we are looking at how high value lithium battery components like cobalt, nickel, and lithium can be recovered in a common existing process. Here, lithium is extracted typically as lithium hydroxide or as lithium carbonate, and these then have to be further processed in a complex conversion process to make the LiPF6, which is the common lithium salt in every existing lithium-ion battery or commercial used lithium-ion battery. Looking at the monetary aspect, we see from this table of the spot prices that LiPF6 price has increased significantly from mid-2020 to the end of 2021. It's sitting around $60,000 per ton, which is quite similar to cobalt, which is chased in most processes. To our process development, our aim was to come up with a practical, economic, and sustainable process which uses common chemical engineering methodology. we wanted to avoid the unsustainable practice of using.
Excuse me, 2 minutes left.
Oh, not more than that. Okay, I leave it there. So what we want to achieve is a high-grade lithium hexafluorophosphate salt, which can be reformulated. And an advantage of our process is that we can do this at the front end of existing processes. Here's a block flow diagram, typical shredder unit at the front end, which is used in other processes. And then the shreds will be leached to extract the electrolyte. The solid phase can then be simply filtered off and be put into existing hydrometallurgical processes. The liquid phase is then treated in a crystallization step where we recover the LiPF6 as a solid material, which can be used for electrolyte reformulation. And the solvents used in the process can be, in principle, recycled in the overall process. So the patent of our process is entering now national phases. We have done many experiments up to 30 gram scale. We have identified the product and the recovery yields are pretty good. Battery testing was done, which was our homework. So making formulations of electrolytes with our salt and then testing them in batteries. And we did also techno-economic analysis. So this is the plot for the battery testing. The blue curve is commercial electrolyte, and the other traces is our system generated with the LiPF6. It stacks up quite well. There's slight differences because the commercially available electrolytes use secret ingredients, which we don't really know of. And techno-economic analysis tells us that the revenue could be $25,000 per ton of the LiPF6 and with a gross profit at around $50,000. So the current state where we are at is the pilot production commences. We've built this shredder unit, which allows us to produce the shreds under inert conditions, excluding air and moisture. We plan to build pilot stage 2, and we are, of course, looking for good collaborations and investment to help this making a reality. And with that, I would like to thank you and all the people who are involved in this exciting endeavor. Thank you.
Thank you very much, Thomas, for your fantastic presentation. Because the other session is still waiting for us to finish. So
Yes.
just one quick question, if the floor has a question. Or any participant online, if you have any question for Thomas, please go ahead. Okay, thank you very much for all of your participation. Thank you very much for our speakers. Enjoy the beautiful weather in Sydney. That's the end of this session. Thank you.